Good afternoon, good morning, and good evening, everyone. Welcome to today's FutFinInfo webinar. I'm very happy to see some new faces in the webinars, but which I recognize from last week's conference under the same name. So there are definitely synergies between those two events. So I hope you will stick around for the webinars if you attended the conference. And today it's my great pleasure to welcome Diego Garcia from the University of Colorado Boulder. So you can see on the clock face behind him that it's still quite early over there. So thank you, Diego, for getting up first thing in the morning to give this webinar. I'm very much looking forward to hearing about the color of finance words. And we also have Byoung-Hyoun Hwang from Cornell, who will give the discussion afterwards. And we will finish off with the Q&A. But if you have questions while Diego is presenting, feel free to type them in the chat window. I will be keeping an eye on the chat, and if I see questions accumulating, I will try to sneak in and put them to Diego so he can answer them as we go. Okay, so with that, Diego, please, the screen is yours for 30 minutes.
Okay, so I guess I'm muted already, Michelle. Okay, great. Thanks so much for the opportunity to present some research in these COVID-19 days. Instead of discussing what to do in the fall of 2020 for teaching, I get to talk research, which is a lot of fun. This is joint work with Hwang, who is a PhD student at CU Boulder, and Max Rohr, who is an assistant professor in the Regression School of Economics, both of whom are here. And all the tough questions are going to go to them. So just really quickly talk about measuring sentiment, and particularly measuring sentiment in finance. There's been a lot of research since the seminal paper by Tetlock in 2007. He was trying to give content to investor sentiment. He did it in the context of the Wall Street Journal versus the market column, trying to predict Dow Jones Industrial Average and using these Harvard 4 dictionaries from the psychology literature. And then essentially right after this Tetlock paper, Loughran and McDonald published their very influential 2011 paper. It's actually one of the most cited papers in the Journal of Finance in the last decade, in which they developed their own bag of words, which is correlated to these Harvard 4 dictionaries from psychology, but they try to incorporate a lot of the nuances of finance and accounting jargon, most notably the word liability, which in most psychology dictionaries were actually considered negative, but of course, is a big chunk of the balance sheet of a firm. And they do the research in the context of 10K statements and stock price reactions to the release. So what is the research agenda on our paper? It's actually very easy to describe, in the sense that all we're going to do is take an off-the-shelf computer science analysis tool, in particular that coming from Taddy 2013, and see whether it has some bite in terms of measuring sentiment vis-a-vis these Loughran and McDonald dictionaries. So I'm going to apologize that the draft is still very early. We just did a major rewrite. We don't actually had to suffer through this. Didn't get the newest draft until last Friday. We're going to focus on this draft on this presentation. I'm going to only present the stuff on earning calls, although we do have in the background some results on 10K statements and media, and I will describe them very briefly at the end. Why did we decide to actually focus on these earnings calls? So we're going to take these transcripts from the earnings calls, and this is your standard CEO, CFO talking to analysts, describing the earnings in the last quarter. We're going to take all that corpora, all those words. I'm going to train a machine learning algorithm on 80% of the data. This is the standard cross-validation technique in this type of using this type of tools. And then once it's trained on this sample, we're going to let it compete. We're going to run regressions on the machine learning algorithm versus Loughran and McDonald on this out of sample 20% that the machine learning algorithm had never got to see. And we're going to do this multiple times and just report averages. And the idea here is we're going to be trying to see who can explain better the contemporaneous price reactions to the release of this information. Let it be earning calls, let it be 10Ks, or just more general financial news. The main punchline is the machine learning algorithm wins every time, and it's not even quite close. These techniques for computer science seem to be having a very big bite. In terms of the ancillary contributions and where we're trying to move the paper is to try to get a better sense of what drives these improvements. And the latest draft, there's a bunch of bigrams and words that these algorithms are picking up. And you're welcome to actually sit down and see how they fare vis-a-vis the Loughran and McDonald dictionaries. So just really quickly again, how do we measure sentiment in financial text? Well, the standard approach, Loughran and McDonald, Tetlock 2007, is to use what is usually referred to as a bag of words approach. So you have a list of words. In the case of Loughran and McDonald, it's a few hundred positive words, a few thousand and some change negative words. We look at our corpora, we count out how many of this occur, and we assign a sentiment score based on that. Now, what are some of the drawbacks of this bag of word approach? It's somewhat arbitrary. At some level, if the psychologist picked it up, there's not an issue. Then there's a probably more important issue, which is the extendability of these words. So the word closed is considered negative in Loughran and McDonald, presumably because if you're closing factories or stores, that's a negative signal. Now, if you actually look at general financial columns from the Wall Street Journal, the word closed shows up literally every day because the market's closed every day in New York in the afternoon. So the word close, of course, has many different meanings. And that's one of the drawbacks of this bag of words approach. And just to give you a little bit of heads up of where we're going, most of this natural language processing literature has started to move away from these bag of words approaches more than a decade ago, and I started working with n-grams. And what I want you to keep in mind is that it's very different to try to give a sentiment score to the word increase versus rate increase versus interest rate increase. Those things have slightly different meanings, of course, depends on the context. And this is what these natural language processing tools are trying to get to capture, going beyond these bag of words approaches. So we're literally going to be borrowing standard tools from natural language processing literature and trying to see if we can actually improve our estimation or empirical fits in financial economics. I will highlight the obvious for those of you who don't hang out with computer scientists. This is a literature that has exploded in the last 15 years together with the increase in computing power. Now we can do lots of things in a couple of hours with our computers that we could not even dream of doing 15 years ago. So just gonna see if these things work in the standard corpora for finance and economics. So what are the research goals? We're going to first try to implement this multinomial inverse regression model. This is a fairly standard computer science technique that is tailored for data of this kind. We're going to train this machine learning algorithm, and then we're going to create, to be able to compare better with existing techniques, we're going to create a set of positive and negative dictionaries of n-grams. And then we're going to focus mostly on bigrams, you'll see why in a minute, based on the loadings generated by this model. So this machine learning algorithm is going to say, these bigrams are positive, these bigrams are negative. We're just basically going to create these different dictionaries and compare them to the existing techniques. And the benchmark that we're going to be using is Loughran and McDonald. In our first draft, we actually did Loughran and McDonald and Harvard 4. The results were essentially the same. And at the end of the day, I'm going to be using these labels, LM for Loughran and McDonald. That's going to be our sort of current state of the art, if you wish. And then I'm going to be using ML, in case it wasn't confusing enough, for the machine learning algorithm. And the whole idea is going to be to compare the performance of these two sentiment tools. Main results, if you look at this auto-sample horse race regressions in which you're trying to predict stock price reactions on the basis of the machine learning algorithms versus Loughran and McDonald, the machine learning algorithm seems to perform much better than the Loughran and McDonald dictionaries. It's interesting to see, and you'll see it in our specifications, that both these unigrams and bigrams have some bite, but the bigrams are the ones that are driving most of the predictability. So we're going to be able to provide what I'm going to call unsupervised bigram dictionaries. And if you think about the approach that we're using here to define sentiment, we're letting the data speak and tell us what are the bigrams or the words that the stock prices seem to react to, rather than being sitting in Notre Dame and trying to decide which words are positive and negative. There's nothing wrong with humans actually classifying words. This is an alternative that is unsupervised and may have some advantages, among others the fact that this can be reproduced by anybody who is listening to this talk, whereas choosing what is positive or negative is going to be a little bit on the eye of the beholder. Okay, so I'm going to skip the literature review, given this is a short presentation. There's a lot of, this is a subfield in finance that has exploded as well in the last 10 years. Loughran and McDonald have a very nice survey of the current state of the art. I'm going to be disagreeing with a few of the things that they mentioned in that survey, but it's a very nice survey in terms of summarizing what we know this far. I will highlight the fact there is a contemporaneous paper by Kelly, Manella, and Moreira that is very related. They also use exactly the same algorithm that we used, Taddy 2013, but it's very complementary. We're using different corpora, we're emphasizing different things. Glasser and Mamaisky have a paper using 4 grams during the financial crisis, 2008, that is also mildly related. And the paper by Jagadish and Wu is also mildly related to our techniques. Okay, so let's just get down to the business. I'm going to be focused on the earning calls. We have a little bit more of a decade. We managed to actually scrape all this data from Seeking Alpha back in the day when Seeking Alpha was actually pretty easy to scrape. We have both the introduction of this earnings call, and this is usually the CEO reading of a prepared paragraph or two, summarizing what they did, and then we have the question and answers as well that the analysts are making to management and going back and forth. And this is a corporate that has been studied in the literature already. We're not the first ones to do it. We have implemented these techniques on 10K statements and also financial news. I do want you to keep in mind that if I think about these 3 corpora, and I've worked with all of them actually in different research projects, I would say there is a pecking order in terms of the signal to noise ratio. And this is something that I was not quite aware of until I started this project. As a finance guy, I always thought 10K statements are very important because Loughran and McDonald designed their words based on 10K statements. Well, it turns out if you talk to accounting people, they say now 10K statements are kind of stale information because typically the release of these 10K statements happens after the earnings call that manager has with this analyst. So most of the information that's getting released when the formal 10K goes through Edgar is information that's already impounded in prices. So there's a lot more information in this earning calls that there is in the 10K statements. And then the financial news that Tetlock 2007 studied, predicting general market movements is very, very hard. So the signal to noise is obviously much smaller there. So we're going to basically focus on earnings calls mostly because we think the signal to noise is the highest out of these three corpora, which is going to allow us to do a little bit more nuanced things that we can do with the other 2 corpora. On the earnings call sample, we have over 50,000 earning calls. I will mention the fact that we are going to be controlling for the usual things, and in particular, the standardized and expected earnings is a main driver of the stock price reaction on these earnings calls. We'll also have size, book to market, and a bunch of fixed effects to stochastic variation. How we cluster standards and so on doesn't really matter for any of our results. We do some data pre-processing. So we clean up, parse, and aggregated text. We do a bunch of other NLP type of cleanings or remove named entities, geographical locations, people, and so on. And most importantly, we're actually going to be using a stemming, which already moves away from what I would call the Loughran and McDonald recipe. If you are familiar with the word lists, they do not stem them. They actually decline every single word and variation, plural, gerund, whatever, participle. The standard approach in the natural language processing literature is to actually stem, because that's going to reduce the dimensionality of your corpora. We're going to go in that direction. I don't think this is actually critical for any of our results, but I do think it is actually best practices. And here, Loughran and McDonald and myself disagree, and we've had this conversation before. There are some advantages to not stemming, but I think the disadvantages outweigh them in our context. Now, if you think about, we're going to be working essentially with bigrams or 3 grams as well in some of the tables. And we have, say, 10,000 or 20,000 documents. If we look and list every single possible engram that has been included in a given corpora, these matrices, the term document matrix or representation of a document explodes really quickly. So we start by reducing the dimensionality of the problem by looking only at the 10,000 most frequent tokens. So we literally take the corpora, list all the words, and pick the 10,000 that are most common. We're going to call that my set of unigrams. We'll do the same thing for bigrams and trigrams. So you can imagine that these matrices start getting very sparse as we move in the n-gram dimension, because there's many bigrams or trigrams that will not show up in any given article. Okay. Now, there's some advantages of having the 10,000 tokens. To start with, we have played around with including 50 or 100, and things do not change very much. This seems to be around the sweet point for this type of corpora.
Sorry, before we move on, just a quick question. Maybe I missed it from the previous slide, but do you exclude any stop words? And if so,
yeah, we will get. I don't know if I have it listed here. Yeah, I do. So we do remove the standard English stop words from standard packages. So I, you, we, have, and the such are going to be removed. It's not a very long list of stop words that we remove. It's less than 100, but yes, we do remove stop words. All right, so really quick, for those of you who are not very familiar with machine learning or artificial intelligence and so on, and I got to admit that this was heresy back when I was in grad school 20 years ago, and now this has actually almost become mainstream. The basic problem is you have n observations of a response variable. Here we have 50,000 stop price return reactions, and then we have 2 million different bigrams. This, a lot more explanatory variables than response variables. So how do we deal with this? Well, these machine learning techniques, what essentially they do is they zoom in and do individual small regressions to try to capture which ones are the words, in our case, that are driving these stock returns. And then we're going to try to penalize overfitting by using lasso penalties. So L1 penalties that will force some of the regression coefficients to 0. Most importantly is this idea of cross-validation. If we just estimate this machine learning algorithm in the whole corpora, then it's going to do a great job overfitting that particular corpora. And the idea is that it has some external validity, and this is what we have, this holdout sample. So we're going to be training on 80%, and then making sure that it works out of sample on data that the algorithm has not seen. We're doing this 80-20, which is fairly standard in this cross-validation exercises. 50-50 works as well as, so if I could probably even works a little bit better. Doesn't make a big difference, actually. So this is the sort of my big picture machine learning summary. This multinomial inverse regression model is one example of this. The basic idea is we're going to have this term document matrix that represents the occurrence of any given token in our corpora. The method has some Bayesian elements to it, but it boils down to try to reduce the dimensionality of the problem into one sufficient statistic, which Taddy calls the variable z, which under some assumptions is actually sufficient. And we're just going to literally take two packages that Taddy wrote in R, text IR, and this trump, to implement his proposed method. And I will highlight this was literally an off-the-shelf implementation. There were a few bugs in Taddy's code, but not many. It was actually pretty easy to implement. Now, what is the key output from this machine learning model? So the sufficient statistics is going to be comprised of a set of loadings on each of these 10,000 n-grams that we started with. Roughly speaking, it's going to say 3,000 of them are going to be positive, 3,000 of them are going to be negative, and then the other 4,000, because of the lasso penalty, they're just going to have a weight of 0, so I'm going to call them ambiguous. What we're going to do with this output is take those n-grams that get these positive loadings, and we're going to throw them into what we'll call a positive dictionary, and then we're going to take those n-grams that get a negative loading, and we're going to throw them into the negative dictionary. We're losing a little bit of information because we're not considering the size of the coefficients, but we think that this is actually a useful approach because that will allow us to map into existing techniques and compare in a little bit of an easier way. So let's get down to the details of the regressions that we're going to be running. So we're going to have the stock price reaction to the earnings calls. The earnings calls also have the advantage that we have a timestamp, so we can be very careful about exactly the price reaction. We're going to have our sentiment score that we're going to construct using this machine learning algorithm, and then we're going to have a bunch of controls. And again, they're not super fancy, but it's what you would expect: SUI, size, and then different year and industry fix effect. The fact that we're dropping the information from the weights in Zissou IT on the sentiment score, not only does it help comparing to Loughran and McDonald, it's also, I think about it, these convolutions that they like to do in this NLP literature as sort of one more layer of last-style corrections, in which we say, well, this got a very high weight, but maybe that was just the lack of the draw for this particular 80% sample that we did. So this is one more way of reducing the dimensionality, if you wish. So I don't want to spend too much time on the actual words themselves. These are the top 100 positive words. Nice quarter, great quarter. There's a bunch of momentum and improvements and a strong. There's a bunch of reallys as well. The team really did very well. But you know, you read through this, and it's actually, we were really surprised with how well these algorithms seem to be picking out things that most of us as English speakers, even if it's a second language, would actually consider positive words. On the negative side, very, very similar. Sort of interesting to see that cash burn is actually the most negative diagram that we found in our corpora. It does sound like cash burn is not a very strong positive signal, and most of the things that you would see here are things that you would probably consider negative words. There is a little bit of overfeeding. I won't lie to you. I mean, it's just part of the nature of the job. Megawatt hour, I wouldn't call that a particularly negative diagram, but by and large, we do seem to be capturing sentiment in ways that a regular reader will call it such. So to summarize, before we jump into the results, which is what I want to finish up the discussion with, is we're going to run n different simulations. We're going to do about 200 is sufficient for our purposes. For each of these simulations, we pick 80% of the sample for training. We construct our dictionaries based on that, and then we're going to save this other 20% for the out-of-sample prediction. And in this 20% out-of-sample prediction, we're going to run individual and joint regressions on returns and sentiment, and then the sentiment, we're going to use the machine learning dictionaries, and we're going to use also these Loughran and McDonald dictionaries. In all the tables, we'll report the average coefficients and t-stats across the 200 simulations. So bear in mind, sometimes you're going to get t-stats of 15, sometimes you're going to get t-stats of 1. So proof of concept. So what we're going to do here in this table, what we do is forget about Loughran and McDonald. Let's just see if this machine learning algorithm works. In the first column, we're going to consider only unigrams, so single words. These are single words that the algorithm is flagging as being positive or negative. And you can see that the predictability is actually very strong with t-stats well above 4, both for the positive and for the negative unigrams. And I think this is one of the contributions of the paper, is showing how one can actually measure positive sentiment fairly well using these techniques. Both Tetlock and Loughran and McDonald in the different surveys highlight how it is much easier to measure negative sentiment than positive sentiment. Our research seems to suggest that both of them are actually pretty easy to measure, at least using these machine learning techniques. So this was with the unigrams, and again, these are just single words. We can do the same exercise using bigrams. So again, we start with this 10,000 top bigrams. We classify them into positive and negative, and then we do this out-of-sample exercise. And you can see that the predictability using bigrams is huge. These t-stats are not made up. It's the same empirical design. And we're talking about t-stats around 9, both for the positive bigrams and the negative bigrams. If you do the same thing with trigrams, and again, the matrices are starting to get more sparse because there's less trigrams that show up in these documents, you still have a fairly healthy predictability, meaning the algorithm does seem to be picking up sentiment as fairly well, both in the positive and negative domain, using trigrams. Now, when you put all three of them together, so try to train on the unigrams, bigrams, and trigrams and do a horse race among them, you can see that most of the predictability is concentrated on these bigrams. The trigrams don't seem to be bringing much to the table beyond what these bigrams are bringing on. And there is some residual predictability as well for using unigrams. So unigrams and bigrams do seem to be complements in measuring sentiment here, although most of the action seems to be coming from the bigrams. So again, this is just a proof of concept. We're not comparing to the existing literature. This is just asking ourselves, can we fit this machine learning algorithm and measure sentiment, and as a consequence, measure the stock price response to these earnings calls using these new dictionaries. So now the next one is going to be our horse race. Let's see which of these dictionaries does better. Does Loughran and McDonald dominate these machine learning techniques? At the end of the day, Loughran and McDonald spent quite some time coming out with this list of words. The first column just shows how Loughran and McDonald dictionaries do in the context of these earning calls. I will highlight that we're using TF-IDF throughout all these tables, which actually helps Loughran and McDonald, as they show in the 2011 paper. So both positive and negative words seem to have fairly strong predictability when considering isolation. Now, column 2 does the first horse race regression, meaning that we're going to try to predict the stock returns now using both the sentiment that comes from Loughran and McDonald and the sentiment that comes from this machine learning algorithm. And you can see here the positive words lose all significance. They were fairly significant in the absence of the machine learning algorithm. Once you put them in, the significance disappears. The negative words still have significant predictive power. The machine learning algorithm, both the positive and negative dictionaries, seem to be performing fairly well. And again, this is just unigrams. We're using only single tokens, not n-grams, that we're going to move to in the next table. What we do with this corpora that is a little bit tricky to do with the others is that we can actually start asking ourselves, well, what is it that the machine learning algorithm is bringing to the table that Loughran and McDonald doesn't have? So what we're going to do now is take our machine learning algorithms and separate those that overlap with Loughran and McDonald and the ones that don't overlap with Loughran and McDonald. So in column 3, we have the Loughran and McDonald dictionaries, and then the machine learning algorithms dictionaries that do not overlap at all with Loughran and McDonald. And you can see that they're both fairly significant. Both significant, meaning that these no overlap dictionaries have a strong predictability, and so does the Loughran and McDonald dictionary. Now, the next column has a slightly different question. I'm going to separate now the Loughran and McDonald unigrams that are not in the machine learning algorithm, and those that have overlap, I'm going to consider them separately. So this is, I'm considering the unigrams that are both in Loughran and McDonald in the machine learning algorithm, and then I'm separating out the ones that are only in Loughran and McDonald. And you can see that all the predictability seems to be concentrated in the Loughran and McDonald words that also makes it into the machine learning dictionaries. Those words that do not make it in the machine learning dictionary have literally zero explanatory power. So essentially,
we have a quick clarification question. So what's the time horizon for these predictions here?
So these tables have a 1-day return, close to close. The results are identical if you do more conservative 3-day windows, minus t minus 1 to t plus 1. So, but I think we're doing this here close to close. Typical day, the earnings call is in the afternoon, so we take the closing price before, and then the next day's price. Now, these results are just for unigrams, and we saw earlier in the proof of concept that bigrams seem to be doing significantly better. So that's the next table is going to be a horse race in which we're going to be running the Loughran and McDonald dictionaries against these bigrams. They're classified as positive and negative from our machine learning algorithm. This is the same results that we had before. Loughran and McDonald do work very well in this corpora. Once you put in the machine learning algorithm, both of them seem to be having some predictive power. It's a little bit stronger on these bigrams. The point estimates, I want to highlight that they have not changed vis-a-vis having Loughran and McDonald, and we'll see why in a minute. When you put everything together, the bigrams with overlaps, the bigrams without overlaps, you see that the Loughran and McDonald still has some predictive power on the negative domain with a fairly healthy t-statistics of -4, but the bigrams with overlap and non-overlap seem to be sucking a lot more of the variation than the Loughran and McDonald. And I will highlight the main reason for this is that these unigrams, Loughran and McDonald is a little bit of a weird comparison. We're comparing sentiment metrics using unigrams, that's Loughran and McDonald, and now we're doing bigrams. So the overlaps are a little bit tricky to do. So there is some marginal value on Loughran and McDonald, though the machine learning algorithm seems to be driving most of this predictability. One can actually do the same specification, but now we're gonna be throwing in both unigrams and bigrams into the mix. So we're gonna have our unigram dictionaries for machine learning, our bigram dictionaries for machine learning. We're gonna separate them into overlap and non-overlap with Loughran and McDonald. And at the top, we actually do have these Loughran and McDonald. And basically this table subsumes our previous results. Once you start considering the machine learning unigrams and bigrams, there is literally no residual value from the words in the Loughran and McDonald dictionaries that are not in these machine learning dictionaries. Literally all the predictability is coming in from n-grams that are associated with these machine learning algorithms. So overall, I think it's fair to summarize and say the machine learning algorithm performs better than Loughran and McDonald. These bigrams do seem to be capturing a lot more than the individual words, although these unigrams do seem to be bringing something. I will highlight here when I'm doing a horse race with bigrams and unigrams, and the unigrams do seem to have some bites. You can see them here in the positive domain, but also in the negative domain, although most of the predictability is being driven by these bigrams. So a natural question where we're trying to go with the paper now is, what is this machine learning algorithm picking up that Loughran and McDonald missed, if you wish? So one of the things that we can ask ourselves is how about the depth of the dictionaries? So we're talking about dictionaries that had about 3,000 n-grams. 500 is more or less what Loughran and McDonald have, at least when you move into the stamped versions. So let's see how sensitive, for example, our results are to having different dictionaries. And this is literally, I'm going to be dropping, and if I have all my positive words, I'm just going to pick the top 2,000 or the top 1,000 or the top 500 or the top 100, if you wish, when constructing these dictionaries. These are the results for the unigrams. Here on the first column, we have about 3,000 and some change. These are the t-stats that we had earlier. You know, there's a fair amount of predictability when you look at these full dictionaries. And when we start reducing the size of the dictionaries, you see that there is a monotonic decrease in the predictability. Okay, so, you know, when you get down to 250 words in the dictionary, the predictability starts being very, very marginal. So we do seem to be losing some information when we reduce the dictionary size with unigrams. Now here is the really surprising result. When you do the same exercise with bigrams, so instead of having 3,000, you go down to 2,000, 1,000, 500, 250, the predictability is still very strong, even with as few as 250 bigrams. I listed 100 in the slides that we had before. That was already, you know, for fairly long list, but you can see that with a few more, you can basically capture all the predictability that we had with 2,000. And even with only 100 tokens, you can see the positive dictionary has a lot of predictability, and so does the negative one for that matter. Now here is another way to compare the Loughran and McDonald dictionaries to what we are doing with this machine learning.
So Diego, I need to say that we're running out of time. So
I don't have my clock on me.
Yeah, please.
Then I'll skip this. The overlap is actually amazingly small between Loughran and McDonald and machine learning dictionaries, and I'll just leave it at that. We have a lot of comparisons in one of the appendixes, and I have shown some slides of this that I will skip. I will highlight one more result, and then I will Michelle, thank you, which is one of the potential problems that we have is that we're using 80% of the sample, and then testing out a sample on 20%. It could be that 80% detects the 2008 crisis, and then we start getting banking words that help me predict what happened in 2009. One can do the whole exercise just looking all the earning calls that happened before, construct your dictionaries sort of backwards looking, and then try to predict going ahead. This is what this graph is doing in terms of the t-stats on Z, and you can see that our results are go through literally as stated when you do these rolling window regressions in which you don't have any look ahead bias. The paper has a bunch of lists on words that overlap and the things that do seem to be together with sort of match Loughran and McDonald and the ones that do not. And I will just end by saying the other two natural corpus is 10K statements and then adverse of the market style news. And the main challenges is that these are actually significantly more noisy. So some of these overlap, not overlap tables that I show you are going to be very hard to actually be able to say much because the signal to noise ratio is not as strong. So I'm going to stop right there. Hopefully have convinced you that these off-the-shelf machine learning techniques can actually be useful to measure sentiment in finance and economics. Thank you.
All right, thank you very much, Diego, for the presentation. And now let's turn over to Byoung for the discussion. You have 15 minutes.
Okay, cool. Thank you very much for giving me the opportunity to discuss this paper. First of all, I'm extremely glad the authors are writing this paper. I think they're starting an important discussion that we need to have. It's funny, like most papers on textual analysis are actually extremely well written. So this paper also is very well written, and I highly recommend everyone to take a look at this. So the way I think or the way I've structured the discussion, let me first provide you a little bit of a big picture, and Diego has done some of that already. There's been an explosion of work doing textual analysis, and part of it is due to a growth in computational power. Like, doing textual analysis is computationally more intensive than just analyzing CompuStat data. So we now have that computational power. Also, there's been a lot more data availability due to online repositories, social platforms. So it's become much easier to analyze text, and perhaps also because we've been looking at accounting stock return data for the past 50, 60, 70 years, I think there's been a lot of interest in taking at this new kind of data. Most of the literature has looked at the sentiment of the text, which I guess you can think of as the first moment of the text, although there's also more and more work looking at the readability of the text. Okay. So there's a little bit of or the authors are starting a little bit of a debate on this. Like, the traditional way we've analyzed these texts is using the Loughran-McDonald way. So they've come up with these dictionaries of positive words, negative words, uncertain words. And so what you do is you just check how often do these words appear in a given text and use that to characterize the text. The authors are saying, well, let's try something different. Let the data tell us what positive words are and negative words are and see what it does better. I spend like a minute on why Loughran and McDonald like their approach. I'll then talk a little, just briefly, because Diego has done some of that already, like why machine learning might be better. And then at the end, so this is me, I guess I'll insert myself and just throw in my own thoughts. So really briefly, why do Loughran and McDonald like their approach, or differently, why don't they like machine learning? Because they're certainly aware of it. And so their main argument is that it's idiosyncratic. The lists generated by computers tend to be idiosyncratic. They don't really generalize. To just give you an illustration of their point is, so I've done some machine learning myself. I analyzed all the text in Seeking Alpha articles, and I tried to then use the text to predict future returns using machine learning as opposed to the Loughran and McDonald dictionaries. And then, so what I find is that machine learning is really helpful in predicting future returns. when you look at the top 5 words that, loosely speaking, most positively predict returns, though, you see this. And the top 5 words that most negatively predict returns is that. So Loughran and McDonald would say, like, see, I told you, basically what you're picking up is just a bunch of firm and industry fixed effects. So that's kind of their beef with machine learning. Now, the machine learning point of view is that, look, these dictionaries created by humans are just way too coarse. You're just missing out on a ton of stuff. And there's some other studies that go perhaps even further and say, look, these dictionaries created by humans are just ad hoc. You have humans inserting themselves into the data generating process that creates all kinds of issues. So here's my view on this thing. So first of all, again, I think it's a really important discussion we need to have, because I don't think there's a question that we're going to continue to do a lot of work doing textual analysis. And so as a user, I'm kind of in the situation, so which way should I go? It reminds me a little bit of these format wars that we sometimes have, like HD DVD versus Blu-ray in 2006. Right? So as consumers, as producers, you're like, okay, which one should we go with? So it seems similar here. I think most people, when they're deciding between LM versus ML, they look at differences in benefits, like which one is more accurate. And they'll also look at the differences in costs, like which one is cheaper to adopt. Let's talk a little bit about the benefits and the costs of LM versus ML. So one way you can capture the benefits, and this is what the authors are doing primarily, is to see which one does a better job explaining how the stock market reacts to the content in the text. And so what the authors find is that if you use ML, like the text that is deemed positive, the stock market actually reacts much more positively to that than a text that per LM, Loughran and McDonald, is positive. So I think I like it a lot. I think it makes a lot of sense. One minor question I have is, so I do consulting for hedge funds. And so this much I can reveal, I think, is that, so they also want to trade on text. And what they're doing is much closer to ML than Loughran and McDonald. They don't do Loughran and McDonald. They do something much closer to what Diego and his co-authors are doing. Okay. So in that regard, I wasn't actually too surprised that the market reaction to is stronger when you classify documents using machine learning, because that's what the quants are doing in trading. So the question a little bit I have is, so let's say there's a text X that is deemed positive, and the market reacts positively to that. Does it mean that the text is truly positive, or is it that just a bunch of quants defined in their programs, this is what a positive text is supposed to look like, and trade accordingly? I mean, I'm sure the quants had their reasoning, but are they right? I'm not entirely sure. And so I think it would be interesting to see whether there's a reversal, but I also think more importantly is I think it's important to look at other measures of benefits. So what could those other measures of benefits be? This, the authors are doing a little bit already. So one thing you can do is you can look at the word list of Loughran and McDonald. You can then look at the word list generated by machine learning and then just look through them and see which one just makes more sense, which one passes the smell test. The authors do some of that already. I guess the problem is when you have like 1,000 words, it becomes a little bit unwieldy. Right? So here's one possible solution that I found in the marketing literature, actually. So there's this paper by Netzer et al. So what they do is they look at this website Prosper. So this is a website where people like you and I can just ask for a loan. Like we describe why we need the money and display some information, and then people can decide, am I going to lend to this person or not? So they do textual analysis using machine learning on the text and see which words predict repayment versus default. And so they also find that machine learning is extremely helpful in predicting whether a person will pay or default. And then to support the argument that their machine learning algorithm makes sense, it's working properly, they have these word clouds. So these are the words indicative of loan repayment. So, and you can see they're very specific. They describe people who end up paying back. They describe exactly why they need the money, events and so forth. And these are the words most indicative of loan default. And you see a lot of reference to God, family, hardship. Right? So the types of words you see in these typical email scams. So after I saw this, I mean, I was already curious when I saw their tables, and the tables looked very similar to the ones presented by Diego. But then you look at this word list and these word clouds, and I mean, that's pretty telling, right? I was sold on this algorithm after I saw this. So I'm wondering whether the authors could do a little bit something like that to further bolster the argument that what they're picking up is actually better. The last thing the authors could do, and I don't know why finance people don't do that more, is just ask retail investors. You could take a text that is rated really positively by their algorithm and negatively maybe or ambiguously by Loughran and McDonald and vice versa. You construct a survey and then just tell retail investors, hey, this text, does it look positive to you or negative? And then you see which algorithm actually better matches how actual retail investors perceive a given text. And it's really not that hard to do. I've tried some of that in my own work. You can recruit retail investors through Prolific and then direct them to a survey, either doing Qualtrics or you can construct your own SQL survey. So if you showed me that in these three domains, ML dominates LM, then I would say it's a pretty convincing argument, but I would say it's hard to argue against that. So my suggestion, I guess, would be, so the authors do mostly this, to work a little bit more on the word lists and then maybe construct a survey. Of course, not on all earnings conference calls. You just pick a random sample of 5% of them, and particularly those where maybe there's a little bit of disagreement between LM and ML, and see. Do 3 horse races, basically. Now, my suspicion is that even if the authors provided evidence that ML dominates LM, people are not going to adopt if the cost is too high. And this may just be a lack of familiarity. At this point, though, it seems that machine learning is costlier to adopt than Loughran and McDonald. So what can the authors do to lower the cost? One thing is, I would love to actually get their data at the document level, right? So this is Brian Miller. He rated the readability of 10K. So on his website, for each 10K, he posts the readability score. And the authors can do something similar. They can provide a program that can be copy-pasted. I don't know, maybe they can even start a service where I send them my documents and you rate them for me and I pay you. That'd be cool. But I think something along those lines, I think, would be helpful to the profession. And just some concluding thoughts. I'm not sure to what degree the authors want to invoke this argument, but so I've been reading textual analysis papers in other disciplines, like MIS, marketing, operations, and of course, engineering, computer science. It appears to me that finance and accounting is the only field that relies so heavily on this human dictionary method. And so I've given talks in front of marketing crowds, engineering crowds, and they think of us as being primitive. Now, having said that, maybe we are primitive, but I guess one thing I do like is about being primitive is it's very standardized. When I look a little bit at the other literatures that use machine learning to a greater degree, some use a version of regularized logistic regressions, another paper uses a different version of regularized logistic regressions. Some people use random forests, some papers use extra forests, some do model stacking and do an ensemble method. So it's like really hard actually to compare different papers. It's become a little bit of a mess to me, at least looking from the outside. So I guess a question, it's almost, it's really a question I would have to the authors is, once we open up to machine learning, how do we maintain some level of discipline and congruence? I think that's actually important for the profession to keep some discipline, actually. that's basically all I have. I think this is an important discussion we need to have, and so I think the authors are providing a service to the profession by writing a paper like this. Thanks.
Right, thank you very much, Diego, for the presentation, to Byoung for the discussion, and to everyone for their participation. So see you in 2 weeks on the next webinar.